How's everyone doing today? Woo. Okay, so my name is Ben, and I'm the VP of Engineering at Chainlink Labs. And I know we've launched a lot of products over the years, and we've launched a few products at this conference. But today I wanted to talk a little bit about a challenging trilemma that we face. And I wanted to give you a bit of a behind-the-scenes look at how we balance scalability, security, and decentralization at Chainlink Labs when we build product. So one thing about the startup tech industry, I think, is that we are very good at celebrating things. And we often celebrate 0 to 1, right? 0 to 1 means going from nothing to something. And people love that. But the thing is, with decentralized services and blockchain Oracle infrastructure, going from 0 to 1 is not the most challenging thing. You can build an Oracle really quickly. And what you do is, you find a data source, you set up a node, and you connect to that data API, you write some code, and you create transactions, put them on a blockchain, and boom, you've created an Oracle. So congratulations, you've gone from 0 to 1, and you've gone from nothing to something. So everyone celebrates that. But is this very good? Can we do better? And I think some people think we can. So what should we be thinking about when we build decentralized infrastructure? Here are the 3 core principles that I think are really important. Number 1, scalability. We need scalability because we want to onboard every user onto a future where applications are trustless and verifiable, and we want these users to come in, right? So security is also really important. If a system is not secure, attackers are going to take advantage of it, and blockchains are really open, they're really permissionless, which means the attackers have an open door as well. And finally, decentralization is the point of this revolution. We can't have any single point where somebody can cheat. So together, these core 3 principles form what is commonly referred to as the blockchain trilemma, and that was originally coined by Vitalik. And what the trilemma really says is that if you stick to simple techniques, then you can get 2 out of the 3 of these at one time. But the third is going to be either compromised in some way, or you're going to have to work very, very hard for it. As an example, you can get scalability and security with just an SQL database. And this has been around for many, many years. But you won't be decentralized. Or you can come up with a really democratic, secure Oracle system that is both scalable, that is both secure and decentralized. But then, if you're going to wait for everyone to vote on every transaction, whether it is approved, then that won't be very scalable. And so this is actually quite a common trade-off and set of trade-offs and challenges in our space when we build. So today, I'm going to share with you a little bit more about how we balance these trade-offs. So the first one that we really need to talk about is decentralization, right? Decentralization is why we're here. And when you distribute control and decision-making power in a network, you get transparency, you get fairness and diversity amongst participants. So back to the story of our basic Oracle service here, we see some common decentralization challenges. First, there's a single source API, single data source, and that data provider is on the left, right? And the data provider may decide over the weekend that they don't want to work, they're going down. Then your smart contract application goes down. Or even worse, the centralized node server may decide that since they have the capability, then they want to change the price on you, and then they can cheat the smart contract. And that's not what Web3 is about, right? Because if the data which is going into the smart contracts is not decentralized, then the system is not decentralized. So at Chainlink, what we've done is to solve both of these problems because we have what we call decentralized Oracle networks. And DONs are run by independent node operators and connect to multiple data sources and providers. So with cryptography and decentralized consensus, we can now create apps that can't be shut down, and you can create apps that are verifiably fair to all the users. But in this design here, there are also some real practical operational trade-offs, right, with DONs. it does look a bit more complex than the previous slide. How do you scale up a new dawn when you have a new blockchain with new node operators? How do you coordinate these node operators when you want to add a new compute job or you want to add a new feed? Now, when scaling up the number of deployments, it's usually very tempting to automate. So in Web2 infrastructure, what you would do is you quickly create a Helm chart, you deploy automatically to a Kubernetes cluster with just a few commands. And that sounds simple. But then you've created a single point of trust, and it's centralization, right? If you have a single entity or location that can change the configuration on nodes, then that's not so decentralized. And so our problem and challenge is really how to balance choice against speed. And I'd like to show you what we built. So this hasn't been shown before externally, but what we've done is we built what we call the Chainlink Orchestrator. And this is a unique deployment service, and it's designed to speed up the deployment of different Chainlink products on different chains. So unlike other services that we have, Chainlink Orchestrator is completely opt-in. So node operators don't need to run it. They can choose to run it, and it's going to speed up the distribution of job specifications. But I think that's a very important design choice and an important pattern to have, because we don't want to force them to install a specific software or to make decisions in a certain way. So this is what the workflow looks like when Chainlink Orchestrator is enabled. The node establishes a connection with the orchestrator, and then the orchestrator can propose jobs to that node. And that job proposal will then show up in the node operator's UI. And then the node operator can review the job proposal, and they can make a choice, right? They must make a choice whether they want to approve or reject the proposal. And they can even set up alerts so that they can get notified rather quickly, so that they can respond to requested changes. But what's important is that the core of decentralization here is that the node operators can and must validate every job addition, and they can and must validate every feed change. Otherwise, there could be malicious changes or updates that slip in. And so we're not automating away any choices here. We're making decentralized choices more scalable. So far, we talked a little bit about decentralization and some of these operational challenges. Now I want to talk a bit about scalability at an architectural level. So at this level and at this design point, scalability is not the exact amount of volume, right, that a solution can support. It's about being able to support more transactions without increasing the fees for the users and the delays that the users experience when they utilize the system. So I have a question for the audience here, and I have a little really rare piece of swag for the first one that gets the answer. So let me ask you, we have two dApps here, and you have the capabilities of the dApps here by transactions per second. And we have dApp A and dApp B, and they all have different properties of what they can serve. So who thinks that dApp A is the most scalable dApp? Can you put your left hand up? Okay. And who thinks that dApp B is the better one? Okay. I think we see a few dApp A's and dApp B's here. And over there has someone picked dApp A, actually. So this is for you. And I'm just going to leave it here so I can keep going. But, sorry. Great. So those of you that picked dApp A would be correct. Why is that, is that the case, right? It's because, most people think about the cost of the first transaction, right? And at first, dApp B looks kind of good. It's $1 per transaction. But as you increase the number of transactions on dApp B, you can see that the cost per transaction is increasing with the load. And that isn't quite a good property to have. So I would bet that dApp A is going to scale better. Similarly, I think we've seen in the past that some blockchains have promised very high TPS. And what happens is that the users come and they use the blockchain, and they're having a great time. It's very cheap to use. And then after a while, as more users join, then the blockchain starts slowing down and need to pay more gas fees. And that's not a great experience, and that's something that we all need to solve together. So what has the industry done together to solve the scalability challenge? Well, from a high level, the blockchain industry is scaling today via what I think is called horizontal scaling, They call it sharding, optimistic rollups, layer 2s, supernets and subnets and so on. And effectively, what this allows new applications to do is that they can get at blockchain in a very inexpensive way, and they can leverage a lower layer for security and decentralization. But why should we care that this is really happening, right? Because we need to think at Chainlink Labs about how blockchains are going to scale and how applications are going to scale. So as an application developer, you have to think, you know, which chain am I going to pick when I develop my decentralized application? Am I going to go on the ETH mainnet and my users pay a bit more gas, but I get great network effects? Or am I going to go for a layer 2? Everyone is going for layer 2. Do I make my own rollup? Or maybe if I want to be on multiple chains, how do I design the application so that I can be on these multiple chains? Do I clone my functionality on every chain, or do I set up, you know, a shell on each one of them, and then I have CCIP or cross-chain messaging to have most of the functionality on a single chain? And so we've been thinking about this problem a lot, and we realized that because chains are going to be so inexpensive to make, and we know that in the next growth period, transaction volume demand is going to go up, well, then that means that hundreds of app chains are going to exist. And as decentralized infrastructure, we can think about every chain as being like its own local network that is going to need Chainlink to survive. Things like data, things like bridges, compute automation, and random numbers, and so on. And so we want to service all these applications wherever they launch, even if it's on their own chain. So this presented us with a challenge. And if you look at this, each one of those boxes there represents a DON. And in the past, Chainlink has created a separate decentralized Oracle network for each data feed on each chain. And remember that DON diagram? Yeah, that's it. And each time we bring online a feed, we need to coordinate these decentralized node operators, right? For example, in this case, if we have 4 feeds on Ethereum, and we want to be also on Avalanche and Polygon, we need 12 DONs in total. Now, that's quite a few DONs. But now imagine if we want to take this same architecture and we want to deploy to 10 feeds on 10 chains, then that means that we're going to need, well, 100 decentralized Oracle networks. And that's a lot of operational work. And if you want to deploy 100 feeds on 100 chains, then that's 10,000 DONs. So our architecture was distributed, secure, decentralized, but not scalable then. So now that we knew we're going to be in a world with hundreds of app chains, I think it's time to rethink how you do blockchain integrations, right? It's time to think about scalability in a new approach. And I would advise anyone that's building a blockchain platform or blockchain infrastructure to also think about this challenge. So we designed an architecture with a more modular, decoupled approach. And if you look at it first, on the left, we have aggregation and signing of low latency reports off-chain. And actually, I thought this was really cool because you know, we actually announced this product, and it's called Data Streams. But we weren't just solving the scalability problem. We were solving also the latency problem. And so you got high-frequency reports, and you know, it's very cheap to have these off-chain reports. And so these are other benefits, right, that we got by generalizing the reports. Now, you can also abstract the transmission delivery from each chain into what we call the transmission DON. And that focuses on delivering the report to every chain. So let's look at some of the scalability properties of this new design. With 4 data DONs and 4 transmission DONs, we can support 4 chains. In the old model, this would have taken 16 DONs. And if you compare this to the case where you want to have 100 data feeds and we need to support 100 chains, then that would just be 200 DONs in total. So that's quite a bit better. The other great thing about this is that adding new chains is also easier, right? You don't have to have a new blockchain built end-to-end, the whole pipeline of a DON. So with this modularization, we have a bit of a network effect growing, right? New blockchains don't need to wait for us to get the data on their chains. By simply integrating a transmission DON, they get access to all the data DONs that are already available. And on the other hand, as a new data provider, if you integrate, we will have access to all the hundreds of chains that we have available. And I think this is a really cool pattern. It's a pattern that allows the Chainlink network to grow in an exponential way. So we've talked a little bit about scalability and decentralization. Next, I want to talk about security as being able to resist against participants and attackers that try to unfairly enrich themselves. So cross-chain security is especially critical because I think this is where most of the hacks, the larger hacks, have happened so far, and it's that more than 2 billion and counting just almost over the past year. And that's because these bridges, they're used to transfer messages, they're used to transfer value, and they've become a target for attackers, right? And anybody in the world can be an attacker, so this is actually the most vulnerable point. Now, when developing CCIP, we wanted to, within Chainlink Labs, have a culture where we reward the risk mindset and the discovery of problems in a positive way. And so we held a pre-mortem. That's different from a post-mortem. It's basically what happens, what can you think could possibly happen? And we convened a risk management committee. And they've come up with a risk register, which has quite a lot of different risks that we've been able to mitigate. But today, I wanted to share just these 4 risks because I thought they were some of the top risks. The first risk with a cross-chain product like ours is node operator key compromise. And the challenge there is that as you scale the node operators and you scale to more chains, you're going to have more node operators, and you don't control how they do security. Some of them are doing it great, but you ultimately don't know how they quite do it. So you have to be worried if the keys are compromised. Next, you got to think about collusion by this type of user class, right? Because there's a lot at stake. And then you have smart contract bugs. That's definitely a risk we want to track and monitor. And fourth, this is something that I think not a whole lot of projects have thought about, but really it's about the single implementation of node software. It's about client diversity. So what our research team has come up with is what we're calling the Risk Management Network, or RMN. And Lawrence is actually going to speak more about this right after that. So if you like the idea, please stick around. But how it works is that it's a completely different secondary DON. And so it's built from the ground up on a completely different implementation in a different language, different frameworks, and different libraries. So for instance, if the Golang library, a crypto Golang library in our primary DON, the committing DON and executing DON was, had a bug in it, then the risk management network would step in and mitigate that bug. Another thing that I think is kind of really awesome about this feature is that unlike if you just have one DON and you keep adding members to the primary DON, the members of the risk management network are only able to approve transactions that they think is good. They're unable to create any transactions themselves. So because we have this risk management network, we can now scale securely without also scaling risk. And we can add risk management nodes without also adding risks associated with node operator compromise. So we now have this secondary DON, and because it flags malicious transactions and is a separate implementation, we remove the risks and we add this client diversity. So the other thing I think that as a pattern that I've seen is that this strategy of proposers and approvers is actually not new. It's quite common in high-value services in Web 2. And I've noticed that often when you're looking at a problem in a decentralized way, sometimes you think that it's completely different. But you can actually go back and see how other systems have worked in the past, and you can adopt them in a decentralized manner. So in summary, I hope I was able to share with you a little bit behind the scenes of how we balance the blockchain trilemma at Chainlink Labs. And in our industry, it's very easy to go from 0 to 1, and we celebrate new launches all the time. It's also easy to get 2 of these, but from 2 to get to 3, there isn't quite an easy way. But I think that if we all come together to build and get the balance right and do the hard work to deliver all 3, then it will be possible for us to build decentralized applications that will be secure and scalable enough so that we can onboard the billions of people and assets onto the next verifiable web that comes. So thank you very much. I hope you've enjoyed this, and if you enjoyed doing this, please come join us. Thanks for your time.